All right, so in chapter 6, so we're in chapter 6. Chapter 6, the first thing that I want to look at is the converting calories to joules. So this is just a conversion problem. So this is the conversion factor that you need to remember. So 1 calorie is 4.184 joules. So this is something that you need to remember. I might write it on my note card. I can't remember if it's in the ALEKS data or not, but you can look that up and see. The other thing is that this question, so we have 9 topics. There are going to be 10 questions on the test. So that means you have to, if you get one wrong, then you get a 90%. So just kind of keep that in mind. I think chapter 6 is a little bit easier than chapter 5. So it's good, but there's still, like, if you miss one, then it can drop your score quite a lot. So in the homework, it's going to give you this hint to round to 3 significant digits. On the test, it's not going to give you that. So you need to remember, well, how are they getting 3 significant digits? So if I look at any of these numbers in the table, they all have 3 significant digits. Okay, so all of my answers on this problem need to have 3 significant digits. All right, so in chemistry and science, we need to measure energy, and that's what this chapter 6 is about, is energy in chemistry. So we often use joules, so kJ is kilojoules. We also, in chemistry, we also use calories. So if you look at the back of a food label, you are seeing kilocalories. So the definition of 1 calorie is the amount of energy it takes to raise the temperature of 1 degree of water, or 1 gram of water 1 degree Celsius. So I don't know if that's in here, but it's in our notes. All right, so we have to convert all of these different units. So they're going to give us 1, and we have to convert it into the other ones. So if we go back to this conversion factor, 1 calorie is 4.184 joules. Another useful conversion factor is I'm going to multiply both sides of this by 1,000, but instead of writing 1,000, I'm going to write kilo. So 1 kilocalorie is the same as 4.184 kilojoules. So by putting a K in front of both of these units, I've just multiplied them by 1,000. So sometimes this is a more useful unit conversion. So either of these we're going to use either of these. So I'm going to start this topic and we'll do one together. So this one, we're going from 1.4 times 10 to the 4 calories. So maybe I'll do it over here. 1.4 times 10 to the 4 calories. I need to convert this to kilocalories. So there's a few ways I can do this. One of these is I can use a conversion factor. So 1.4 times 10 to the 4 calories. And I know I need kilocalories, so kilocalories is going to go on the top. And I can look up in my ALEKS data. So we can do that. It just takes a minute to load. But kilo means 10 to the 3 calories. So basically, I'm just dividing this by 1,000. SI prefixes. So kilo, K, little k, is 10 to the 3. 10 to the 3 little units. So instead of writing K, I can write 10 to the 3. All right, so if I divide this by 1,000, I will get my exponents will cancel out, and I'll end up with, I think, 14. Okay. And then my units cancel kcal. So another way we can do this is we can take this number, 1.4 times 10 to the 4, and we can write this out. We could do 1, 4 1, 2, 3, 4. And then divide by 1,000 because we're trying to get 2 kilocalories. 1, 2, 3. We're back to 14. So when I type this in, it needs to have 3 sig figs. So it'll be 14.0. And then if I'm trying to convert to kilojoules, I can take either of these numbers. I'm going to use the kilocalories. So let me scoot this up a little bit. I'm going to use 14.0 kilocalories, and I'm trying to get this unit into kilojoules. So then I'm going to use this unit conversion factor that says 1 kilocalorie for 4.184 kilojoules. And kilocalories cancels, we end up with kilojoules. And then that will be my answer. So I will type this in on the ALEKS calculator. So 14 times 4.184, and that gives us 58.576 kilojoules. We need to report 3 sig figs, so this will be 58.6 kilojoules. All right, so the next one, we're going from kilocalories to kilojoules and kilocalories to calories. So if I'm going from kilocalories, I have 125 kilocalories, and I'm trying to get to just calories. I can move my decimal 3 to the right, so I'm multiplying by 1,000. Or I can use that conversion factor, 125 kilocalories times by, I know that I have 10 to the 3 calories per kilocalorie, and kilocalories cancels out. And then we have 125 times 10 to the third. But remember, for scientific notation, we have to have just one decimal place. So I'm going to move the decimal 1, 2 to the left. So I have 1.25 times 10 to the 5 calories. Times 10 to the 5. Okay, and then if I'm going from kilocalories to kilojoules, I'd take my 125 kilocalories. I multiply by this number, 4.184 kilojoules, my conversion factor. Oops, there we go. Per 1 kilocalorie. Kilocalories cancel out, and we end up with, let's see, 125 times 4.184, and that gives us 523. And let's put a decimal. All right, so this last one, we're going backwards. So we have 460 kilojoules. We need to get that into kilocalories first. So we need kilocalories on the top so that it ends up at the end. And then we need to cancel out kilojoules, and it says 4.184 kilojoules per kilocalorie. So remember, that's just our conversion factor. So kilojoules cancels, we'll divide. Four 460 divided by 4.184. That gives us 109.9. So then we need 3 sig figs. Oops. So I'm going to round up to 110. Let's see if it'll let us just put in 110. That's a really annoying number. Okay. If not, we'll have to put it in scientific notation. Okay, so just notice that this trend is that the middle number is kind of in the middle. It's the lowest. These numbers should be the lowest. They should be proportional. So just watch. So if this number ends up being bigger than this number, you did it wrong. So just watch your trends. And then this number often has a scientific notation number because we need a really big number to represent something with a big prefix. Okay, so then we need to go from 110 kilocalories to, we need to get to just calories. So we need to multiply this by 1,000. So basically we're just moving the decimal 1, 2, 3. And so then if we move our decimal back 1, 2, 3, 4, 5, we have 1.10 times 10 to the 5. Okay, so let's see what we got. Okay, all right, so that was good. It let us put 110 with a decimal. All right, so that's the first type of problem when it's just a conversion problem between calories, kilocalories, and kilojoules. All right, the next one I want to go over is this interpreting an energy diagram. So let's look at one of these problems. So we have a chemical reaction where we have our reactants going to our products, and we don't really know what they are, and it doesn't matter. So if we look at this graph, we have some important things going on. So first, whenever we look at a graph, we should look at the axes. So we have on the left, on the y-axis, we have energy. And also notice the units. It's in kilojoules per mole. So we just talked about the mole. And we also talked about how we use kilojoules for energy. Okay, the other thing that we see is we have this line with A plus B. So remember, A plus B is our reactants. And we also have our products over here, C plus D. And we also have this kind of curve thing, okay? So along this part is called the reaction coordinate. This is called a reaction coordinate diagram. They're also calling it an energy diagram. So this is where we start, our reactants start over here, and our products end over here. So notice that our reactants here in this graph are higher energy than our products. And that tells us something about our reaction. The other thing we have in this graph is this is called, from our reactants to the top of this hill, to the top of this curve is called the activation energy. So this activation energy is how much energy we have to put into our reactants before they can start going down the hill to getting to our products. So this is kind of like doing a chore. We want something done, but we have this energy barrier or activation energy before we can get to the products. And this top point is called the transition state. So that's just the highest point of energy in the reaction. Okay, so when we are looking at this problem, we're looking for the heat of reaction. So the heat of reaction is always, we use delta H to say the heat of reaction, delta H. The heat of reaction is always the energy of the products minus the energy of the reactants. So when I'm looking at the graph here, the energy of the products is 150. So that's like right here on our graph, 150. The energy of the products is 150 kilojoules per mole. And then the reactants is way up here at 300. Okay, and it should label it. If it's going to ask us to do math, it has to label those numbers. Okay, so 150 minus 300, and this one we need to make sure we're watching our signs. The signs are really important. So 150 minus 300 gives me negative 150. Okay, and then I just type that in. The heat of reaction for this reaction is negative 150. All right, so if our graph looks like this and our products are lower than the reactants, we are going to get a negative heat of reaction. If delta H is negative, then that's going to be called exothermic. Heat is released. So I like to think of this as energy is exiting. We have negative energy. Energy exits. Okay. If this is flipped, we'll look at another one. If it's flipped, then delta H is positive. That's called endothermic. And that is where heat is absorbed. So if you have had a cold pack, that's a reaction where heat is absorbed. You can feel it leaving. And then energy enters. Or you have to add energy for the reaction to go, or to get to the products. Okay, we always have that activation energy that we have to add energy to. All right, so let's look at the rest of the question. So this one we decided because it's negative, it's exothermic. Can we determine the activation energy? So remember, the activation energy is between the reactants and the transition state. So here we can see the transition state as at 400. So we're going to say the transition, so 400 to our reactants, 300. 400 minus 300 gives us 100. And this one's always going to be a positive number. Can we determine the activation energy? Yes, it is 100 kilojoules per mole. Can we determine the activation energy of the reverse reaction? So the reverse reaction is where we switch the order of the graph. So we imagine that we're starting at the bottom and we have to go all the way up to the top before we can go to our products. So this would be an example of, we would have products. Now our reactants are our products. So we'd have our products. 300 minus 150 would give us a positive 150. So this heat of reaction would be, from going in the reverse reaction, would be endothermic. Okay. It wants the activation energy. So it wants the activation energy, which is from our reactants. Remember, this is the backwards reaction. So reactants to our transition state. So it would be, so if we're looking at this, remember this is 150 to the transition state, which is 400. So we would do 400 minus 150. Okay, and this, again, the activation energy is always going to be a positive number. So yes, the activation energy of the reverse reaction would be 250 kilojoules per mole. Okay, let's look at one more of these ones. Let's see if we can get an endothermic. Okay, good. So this one, when we're doing this problem, we have our reaction coordinate diagram. The products are at, let's see, our reactants are down here at A plus B. Our reactants are at 150. And our products are at 200. And then the transition state is up here at 350. So the first question it asks is, what is the heat of reaction? So remember, heat of reaction is delta H. Heat of reaction is products minus reactants. So products are at 200. Reactants are at 150. The difference there is just 50. and it's a positive 50. So sign the negative or positive is really important here. So this one is positive 50. If it's positive, then it's endothermic. And heat is absorbed. Heat is added to the reaction. And then can we determine the activation energy? Well, we're looking from our reactants, or excuse me, reactants to the transition state. So reactants to the transition state. And this one is always going to be positive. So we have 350 minus 150, which is 100. Is that right? No, that doesn't sound right. Okay, it's 200. Excuse me. All right, so yes, we can figure out the transition. This is always going to be yes, unless you don't have numbers on your graph, which is not going to happen. So all of these are always going to be yes, so figure it out. So this one says determine the reverse reaction activation energy. So we're going from now, so we usually read it going this way. Well, the reverse reaction can also happen. It's just going that way. So we start now, this is our reactants. This is still our transition state. And so we just read off. So this would be 350 minus 200. That gives us 150. And this, again, this is always positive. Okay. All right. Next question is drawing the reaction of energy diagram of a catalyzed reaction. So this one, what happens in a catalyzed reaction is the only thing that changes is the activation energy decreases. So for this problem, we need to know that an exothermic reaction looks like the reactants are lower than the products. For an endothermic reaction, the reactants are lower than the products. We have to put energy in to get to our products. Here we are losing energy in an exothermic. And remember, an exothermic reaction, the heat of reaction is negative, and here the heat of reaction is a positive number. So the other thing we need to know is for a catalyzed reaction is for the catalyzed reaction, the only thing that changes, the product's energy stays the same, and the reactants on the products stay the same. The only thing that decreases is the height of this barrier. So if it's catalyzed, this is going to be easier to get to the products. So a catalyst doesn't participate in the reaction. It just makes the environment of the reaction easier. So it's not a product, it's not a reactant. It doesn't get consumed, but the catalyst just makes it easier for the reaction to happen. So if we had a catalyzed reaction over here, the reactant's energy would stay the same, the product's energy would stay the same. We're just changing that energy barrier. It's a lower energy barrier if you have a catalyst. So in this one, it says we have an exothermic reaction. So remember, for an exothermic reaction, the products have to be lower in energy than the reactants. So it doesn't matter where you put this. You just have to have enough space that you can change the activation energy. So uncatalyzed, here's my activation energy barrier. Maybe I want to make it a little bit bigger. It doesn't really matter. And then I have to make sure my reactants are at exactly the same level. So use that line to tell you. Reactants are at the same level. Products are at the same level. And then if it's catalyzed, the activation energy barrier is going to be less. And it's just looking for qualitative. It doesn't matter exactly where you put it. You just have to know, it means the reactants are at the same energy. The activation energy is lower. Oh, my products weren't in the right spot. There we go. Okay, now recheck. Okay, so that's a pretty easy topic. So just make sure that your levels are the same, and then your activation energy decreases for the catalyzed reaction.